Hello, folks. This is Mr. Tolbert's class here, and it's actually we're going to be going over chapter 14. We'll be starting the first lesson in chapter 14. It looks like I looked back at my lesson and the audio didn't work, so I'm just re-recording this first part right here. So let's see what we have going on here. So this is chapter 14, and this is the first lesson of chapter 14.
Eureka! And the third and final program in this unit, we know that everything is made up of molecules. That tree, the plastic cup, the magnifying glass, this piece of lead pipe, even you are made up of molecules. Does that mean that molecules are all the same? In that case, why do glass cups break when you drop them, when plastic ones don't? On the other hand, why can't you see through a magnifying glass made of pink plastic? Or chop down an aluminum tree with a rubber axe? If all these things were made of identical molecules, how could they all be so different? If everything around you were constructed with exactly the same building blocks, it'd be like living in a world of Lego. So molecules can't all be the same, can they? What are molecules made of anyway? We know that they're little lumps, but little lumps of what? Of course, there's no magnifying glass powerful enough to let you see molecules. They're much too small for that. But scientists now know that if by some miracle you could look closely enough at a typical molecule in plastic, for instance, you would see that it isn't a solid lump at all, but a lump of thousands of tiny round things all jiggling about together like a bunch of grapes going bananas. Scientists call these tiny round things atoms. But notice that not all the atoms are alike. Some are big and some are small. Some have a lot of mass and some have very little mass. Now let's look at a typical molecule in glass. It's completely different from a molecule in plastic. There are only 3 atoms instead of thousands. And therefore, a molecule in glass is much, much smaller. And that's why something made of glass can behave so differently from something made of plastic. Let's zero in on something made of metal now. The head of an axe, let's say. And see what a molecule of iron looks like. Ooh, that's strange. The whole axe head seems to be just one giant molecule, because the atoms aren't bunched together in lumps at all. They're all independent of each other. In a sense, there are no molecules in iron, only separate individual atoms, all of them the same size and all arranged in a square-shaped latticework. Now let's look at something made of another sort of metal, a lead pipe, for example. In lead, the atoms are also all the same size, but they're much larger than in iron. And they're more tightly packed within their latticework. But they're still separate, individual atoms. So strictly speaking, there are no molecules in lead either. In fact, there are no molecules in any pure metals. Iron, lead, aluminum, copper, silver, gold, you name it. They all consist of separate, individual atoms. But all substances in all 3 states of matter, solid, liquid, and gas, are made up of different combinations of atoms of different sizes and masses. Either arranged separately, as in all pure metals, or bunched together into molecules, as in most common nonmetals, liquids, and gases. So next time you chop up some wood, or feel the weight of a lead pipe, or drop an unbreakable plastic cup, remember the enormous variety of different combinations of atoms that makes all this possible. And be thankful you don't live in a world of Lego.
So yes, as you can tell, this unit is basically atoms. We're going to break down the things that we know about atoms and become more understanding of how we use atoms, the basic parts of atoms, and how do you make those molecules. It's John Dalton. John Dalton was not the average man. In fact, he was in school till he was 11 years old. Then after he was 11, he quit, and then he came back as a teacher, which is crazy. I could not imagine doing that. But in 1794, he became the first person to publish a description of color blindness. And he actually suffered from color blindness. And that's also an interesting little piece because he was also a chemist. And because he was a chemist, it made it also difficult for him to see the little changes like color changes because he was colorblind. So a lot of people said he was rather clumsy because he was colorblind, clumsy as an experimenter because they couldn't see some of these color changes that we take for granted. So there are some things that we earmark as Mr. John Dalton. We earmark color blindness, as sometimes referred to as Daltonism. He was remembered as the one that took over 150 years of research and other forms and come to the conclusion that all of these things that we thought were separate were made of atoms. So let's break it down a little bit further. Dalton is another name for a couple of these things. You might want to keep these things in mind because they are very important. Looking over to this, oh yeah, there we go. Looking over this side, can I get that finger? Yeah, you got, oh, that's cool. You got A, B, C, and D. Okay, so you got great great scientists, a color blindness, atomic theory, and not being an average man. Okay. In order to understand atoms, we have to understand what actually holds all these things together, what we call the electrical charge. So let's move this down so you can see it. We know of two different kinds of electrical charge. We call them positive and negative. We know that opposites attract, whereas the positive is attracted to the negative. Or if they're like symbols, like you see here, they're going to repel each other, and the two negatives are going to repel each other. We say an object is electrically neutral when the total electrical charge is zero. Looking at this example over here, you've got 8 positively charged little circles here in red, and you have 8 little negatively circles here in black. The net charge is 0. So the positives cancel the negative, giving us the grand total of a neutral charge. Early model in 1897, English scientist J.J. Thomson discovered that using these cathode rays and these different tubes, you're able to pass particles through and you're able to do a bunch of different things, okay? And that's where we came with this whole concept called electrons, okay? He called these little guys electrons, but actually he didn't coin it as exactly as electrons. And I'm going to show you a little video here coming up that's going to give you more information about the electron. But he did come up with this here original model where he is called the plum pudding model, in which case he thought the whole outside of the electron was positive and the electrons were these little negative pieces of fruit, if you will, inside of his food. All right, so this is where I'm going to stop my lecture. I'm going to play one more video. It's about 5 minutes, so I'd like you to go ahead and watch this. Then you're going to answer some questions. So the first assignment for this particular week is to watch this video, and the second assignment for this week is to answer some questions, okay? So Ernest Rutherford and friends came together with this gold model, this gold foil experiment, and it is how we discovered that things were mostly empty space. But without further ado, I'd like to go ahead and show you the breakdown of the nuclear model, or the crash course of a nuclear model. Okay.
How do you picture an atom in your mind? Like this, or like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, you know more about atomic theory than the scientists did just 100 years ago. and like way more than...
Come on. Sorry, guys. I don't know what it's doing. Just needed to play.
How do you picture an atom in your mind? Like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than the scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly... They didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms, so they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode rays, which is the work of generations of previous scientists. Because the fact is, atomic theory as we know it is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But as is in all science, each scientist built on what had been learned before. We've been talking a lot about the fine details of chemistry in recent weeks, and we're going to keep doing that as we move on to nuclear chemistry and then to the basics of organic chemistry. But before we do, I wanted to set aside some time to explain how we know what we know about the atom today, and how we know that we're not quite done figuring it out. Developments in atomic theory didn't come along for nearly 2,300 years. I told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same. And you should remember the English teacher James Dalton, who determined that elements exist as discrete packets of matter. Thanks to these and other great minds by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. Basically what a neon light is. Because the light was originally produced by a negative electrode, or cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he discovered here. I mean, scientists still haven't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the charge tube research further. By measuring how much heat cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thomson visualized this model as a familiar English dessert. Plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. Right. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium. They were positively charged and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area, an area that he called the nucleus. Because most of the alpha particles pass right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly responded that these tiny positively charged ions were themselves fundamental particles, protons. Now we're getting close to reality. So these chemists had a fairly good idea of the structure of the atom. They just needed to figure out what exactly the electrons were doing. Enter Niels.
All right, so that brings us to the end of this particular little lesson. Okay, I hope you've enjoyed our little lesson for today. And all I need you to do is go ahead and watch this, and there will be some questions that we'll answer that'll be right there on Schoology. Have a great day.